Okay, so this is part 2 of equilibrium. Here we're going to be looking specifically at LaShawn TJs principle, which is just going to account for how a system is going to react to an applied stress. And so if we adjust the pressure, the temperature, the volume, or something, what's going to happen to that system? And then finally we're going to get into some more specific calculations here. Okay? Now, if we look at LaShawn TJs principle, LaShawn TJs principle simply says that if a system at equilibrium, meaning it's already got consistent, stagnant concentrations of reactants and products, while the forward and reverse reactions are occurring simultaneously at similar rates or the same rate, if a system is at equilibrium and subjected to a perturbance, the position of equilibrium is going to shift to counteract. Think of this in terms of a scale, okay? So you've got your little plate here, you've got a little plate over here, and if you shift this, you come over and you knock into it or something like that, it is going to wobble back and forth until it reaches that same ratio of what's over here to what's over here. It is going to allow for equilibrium to be maintained, the same K value to be represented just by a shifting in the equilibrium concentrations. Now for us, we're going to have shift primarily in one of three ways. We're either going to have a change in concentration. That means we could be adding something in. We could also be adding something or taking something out. Either way, we could have a shift in temperature. A shift in temperature is the only thing that will actually change the K value. The K value should be pretty consistent across the board otherwise. And then finally, it could be pressure. Now, adding an inert gas will not affect equilibrium whatsoever, but you can adjust the pressure of a closed system and it will shift slightly. This should be reactant. I forgot to upload it. So consider the endothermic reaction we have here. Endothermic means that you have to add in heat on the reactant side to have the reaction go forward. And so when we talk about this reaction, we're going to consider heat as a reactant. So if we add increased reactant, that means we're going to be adding in a lot of our Br2 in order to shift to make that K value for Br2. We're adding in a bunch of this. In order to shift to make this equal, we have to allow for the more production of product so that the K, or the ratio of product to reactant, is going to be the same. So it's going to shift, right, it's going to make product so that the ratio is going to be the same between reactant and product. And if we make product, if we add in a bunch of product, we dumped in some Br gas, then our ratio is going to be shifted because now we're going to have some of this top amount going up. And so in order to have that K value equal to the same, you have to basically go back the other way. You're adding in some of this, so it needs to go here. That is pretty much exactly the opposite of what we just said. So whatever happens, you've got to account for that. What is this? How do I get rid of this? By a shift in the equilibrium. The point is that the amount of reactant, the amount of product, isn't going to reach the original, but it's going to reach the original ratio. Now, if we were talking about a product, if we were talking about a reactant or a product being decreased, meaning you remove it, that is going to allow for a shift to make some of what you have removed. You ever had somebody, you're carrying in grocery bags or something, somebody comes and grabs a few for you, well, then you pick up some more, so you still have basically the same amount of weight. So if you decrease reactant, you take some of this out, you've lost some of this bottom, so you're going to try and make more. So we are going to shift to the left to make more reactant so that that ratio is again the same. You decrease product, you're going to want to increase product. The idea being you have to go back to those original concentrations. In terms of pressure, now guys, if you add an inert gas, nothing's going to happen to the equilibrium. But if you have a closed system and you shift pressure, if you increase pressure, think of it in terms of if you know you have a certain amount of space, you're going to try and fill it accordingly. If you increase pressure, you're going to go to the side with fewer gaseous components. Here we have 1 mole of a gas. Here we have 2 moles of a gaseous compound. And so if pressure is increased, here we're going to move to the left because it's got the side with the fewer moles of gas. If we decrease pressure, all of a sudden you could have a shift that allows for a slight addition of product because again, there we go, because it's going to have room for more of that gas. And keep in mind when you read about the KP and molarity and pressures are correlational, they're about the same. So just kind of keep that in mind as you go. Here we have an endothermic reaction. So if we raise temperature, we're adding in reactant. So in order to have a shift, you're adding in reactant, it's going to move to the right. If you lower temperature, it's going to try and make more heat. It's going to try and make more of that reactant, so it's going to make more towards the left. If we consider an exothermic reaction, everything is the same except for now we are going to be treating heat as a product. Heat is going to be exiting or leaving the system, okay? So because heat is leaving the system, if we raise temperature, we're adding in product. It is now going to shift to the left to get rid of some of it. If you lower temperature, it's going to try and make more heat, which is going to shift to the product side. The idea is no matter what you do to the system's going to kind of try to do the opposite so that you end up getting the same ratio, the same type of things happening as the original situation. Now, that means if you if you add in concentration, it's going to shift away from the added component or it's going to shift towards the component that's removed. Either way. In terms of temperature, K changes with temperature. It's the only thing that can change your K value. Now, depending on whether you are exothermic or endothermic, will also shift which direction. The idea being it's going to go towards the added component or away from, or going towards the, let me start that over. It's going to go away from the added component or towards whatever was removed. There we go. In terms of pressure, if you increase pressure, if you add in gaseous component, it's going to shift away from it. If you remove a gas component, it's going to shift towards that gas component that was removed. If you add an inert gas, nothing changes. Decreasing volume is going to shift to the side with fewer moles of a gas. Now, in terms of equilibrium, once it's is at equilibrium, things do not, the K is going to be constant. But the idea is, how do you know if you're at equilibrium or not? And so one of the ways that you can know is by looking at the reaction quotient, which is a given, the same ratio. It's still going to be products over reactants, each raised to their exponent. So this would be K is equal to concentration of B over concentration of A squared. But the idea is Q is for any given period of time. And so you can take a Q here, here, or you can take it out here. And so the idea is if Q is equal to K, you are at equilibrium and nothing's going to change. If Q is less, well, let's start up here. If Q is greater than K, it means you have more products than reactants, and so it's going to shift to the left to make more reactants. If Q is less than K, that means you have more reactants than products, and so you're going to try and make more products just to get that ratio. You want Q and K to be equal. Now, in lab, you guys are going to be dealing with a problem like this, where you have iron, you have thiocyanate, and you're going to make a complex. Now, what's really cool is this is kind of like a light yellowish orange, depending on the acid they use, and this is a really dark red. And so you can kind of look at a reaction, whether it's reactant-based or product-based, just by color. And so if it stays orange, or a yellowish orange, really, it's reactant-based. If it turns a really dark red, it's product-based. And you can tell that very quickly, and you can kind of estimate, oh, well, if it turns red, K must be very large. But, you know, you'll see that in lab. Now, here, this is a very typical problem. You're going to have initial concentrations, and you're going to have one equilibrium concentration. And then you're going to try and back calculate to find the concentrations of everything and then calculate your K value. Now, I kind of need more room, but I think what I'm going to do is write it up here instead. And so if we have Fe3 plus SCN going to FeSCN. Now, the way that we talk about this is usually with an ICE table. ICE means initial, then there's some change, and finally you reach equilibrium, okay? So let's look at what we know. We know initially we have 6 molar iron and 10 molar SCN. And initially, if you're just mixing in the reactants, you don't have, any product. So this should be a 0. I forgot I can do my eraser that way. Now, meanwhile, they then tell us that this is 4 molar. Now, we have to find our equilibrium concentrations to plug in for our K. Remember, K is going to be products, which is FeSCN, over reactants, which is Fe and SCN. Now, we know this guy, but we don't know these two, so we need to find that. Now, let's look. How do you go from 0 to 4? You add 4, right? It's an add 4. Don't overthink it. Don't underthink it, but don't overthink it. Now, remember, guys, these are all concentrations in molarity, which is what we're going to plug in. In lab, sometimes you'll do it in moles and then convert it to molarity at the end, so just be aware. As long as you're in molarity when you plug it in, you're okay. Now, here, we added 4 moles of FeSCN. 4.0 moles per liter FeSCN. We know, according to this reaction, if we have 1 FeSCN being made, we had to use 1 Fe, right? So that means we used 4 molar, 4 times 1 divided by 1. We used 4 molar iron. Same thing, we could plug in the same thing for an SCN, 1-to-1 ratio, so it's going to be -4 here. So 6 minus 4 gives us an equilibrium concentration of 2 molar, and here it's a 6 molar. Make sure you are using your mole-to-mole ratios to find these numbers. So this gives us, we plug in our equilibrium concentrations to find our K, 4.0 molar over 2 molar and 6 molar. 4 over 12 should be something like 0.33. Oops, no units. Now this is probably not what you're going to see because we wouldn't talk about colors if it was a reactant-based reaction. It should be a very large K. If you do it right, it should be on the order of about 150. But it's a good way to look at this. So make sure you are setting up your ICE table for all of these problems where you're looking at what is being added of products, what is being subtracted from reactants. Or if you have all products, you could go backwards and then you would lose here, add here. It's just that on the other side of the arrow, the opposite is going to be occurring. There we go. So when doing these problems, find the balanced equation. If it's not balanced, you're not going to have the right K expression, and your numbers are going to be wrong. List your initial concentrations, and then you can calculate Q if you need to determine how it's going to shift. Or, more importantly, figure out how you're going to have a change occur. Then we're going to find our equilibrium concentrations, plug them in, and you're going to find your value of K. So here's a pretty legitimate problem. We have a 2 mole sample of ammonia and it's introduced into a 1 liter container at a certain temperature. The ammonia partially dissociates. At equilibrium, 1 mole of ammonia remains. Let's look at this really quick, guys. I'm actually going to see if I can man, nothing. All right, well, never mind. I was going to try and raise this so I had more room to do my ICE table, but I'll just do it up here. So ammonia dissociates to give us N2 and H2. First things first, this is not balanced, so we have a major problem here. I have N and H, 1, 3, 2, and 2. Fixing my N's, I need to add a 2 here. Makes this 2 and 6. To fix this, I'm going to add a 3 here. Let's go ahead and make this neater so you guys can follow along. So now I have my nice, neat reaction of 2 ammonias dissociating to give N2 and 3 H2. Now we do need to consider our ICE table. So we're going to have initial, change, and equilibrium concentrations. Now this is giving it to us in moles. I'm going to go ahead and leave it as moles, understanding that our K has to be done in molarity. So K is going to be products over reactant, so it's N2 times H2 cubed over NH3 squared. Now, so this is going to be 2 moles here. We know initially if we have reactant, we don't have any products, so there's 0 and 0. At equilibrium, we're left with 1 mole. So we have here a change of X, or really 2 minus 1 gives us 1 mole difference. Okay. Now, this is not as nice and pretty as it was before, because if we have 1 mole of NH3 that we used, every time we have 2 NH3 moles in the reaction, we make 1 and 2. So we're going to have half as much of this made. 1 times 1 divided by 2. This is going to be plus 0.5 moles. For the other 1 mole NH3, we know every time we have 2 NH3, we have 3 moles of hydrogen. So this is going to be plus 1.5 moles here. So at equilibrium, we now have all of these moles. 1 mole, 0.5, 1.5. We can't plug molarity into here. We need molarity. So we're going to come back and divide by the volume of the container, which fortunately leaves everything the same. So at this point, we can now plug in to our K value, and we have 1 point, well, actually, let's do it in the right order. For N2, we have 0.5 molar. For H2, we have 1.5 molar, but it's now going to be cubed because of this 3. And all of that is going to be over 1 molar squared because of the ammonia being squared. And if we plug this into your calculator, again, this is one of those situations where it's very easy to be like, well, of course I have the right answer. And make sure you're actually getting the right answer, guys. You should be getting something like 1.69. That should be your K value. If you are not getting that, either email me, come see me, we have to figure it out. Oops. There we go. Last way that this can be calculated. I don't know. Okay, this is a 1 mole sample of N2O4 is placed in a 10-liter vessel and allowed to reach equilibrium. Find the equilibrium concentrations. This is also pretty legitimate. So I'm going to go ahead and write up here what we already know. This is N2O4 reacting to make 2 NO2s. If we look, 2 and 2, 4, and 2 times 2 is 4. So this is already balanced. Here, we know that K is equal to NO's concentration, NO2 concentration squared, over N2O4. And that's equal to 4.0 times 10 to the minus 4. Now, we have a 1 mole initial change equilibrium amount of this added. And initially you have zero product. Now we have to go through some change. And even without going too far, we know that whatever we lose over here, we're going to create 2 of them over here, 1-to-2 ratio. So at equilibrium, actually, you know what? We're going to go ahead and put this in concentration. Let's show it. We just showed you with moles being first. Let's go ahead and put it into molarity. Okay, so we have 1 mole, which is here, in a 10-liter vessel, which gives us 0.1 molar. So at equilibrium, we know we have 0.1 minus x, and over here we have 2x. That's pretty legitimate. But if we try to plug that in, if you look, that means that we now have 2x squared over 0.1 minus x. That is a nightmare. Now you can totally solve for your x value, by doing the quadratic equation. For the most part though, guys, I don't care. The idea is chemists are lazy. We're going to make an assumption that is going to work all the time and give us less than 3% error. So let's look at that. So if you look here, K is 4.0 times 10 to the minus 4. This is 0.1. This is so much smaller than the reactant concentration of 0.1 that 0.1 minus X is pretty much the same as 0.1. Okay? So when we're doing this, we're going to assume that 0.1 minus X is 0.1. And we're going to plug it in as 4.0 times 10 to the minus 4 is equal to 2x squared over 0.1. Multiply both sides, it's 4.0 times 10 to the minus 5 is equal to 4x squared. Divide both sides by 4, you get 1 times 10 to the negative 5 is equal to x squared. And then to get the next step, you're going to take the square root of 1 times 10 to the negative 5. And you should get x is equal to something like 0.00316. So if we look at this, we can go back and calculate the concentrations of these. 0.1 minus x is equilibrium concentration of here. Where am I going to solve this? 0.1 minus 0.00316 gives you something like 0.968, which is about 0.1. So that assumption holds valid. 2 times x gives you ends up being 0.00632. So we now have our equilibrium concentration of both of those substances. This ends up being really fun. You always have, if you get in a situation where it looks like you're going to have to use the quadratic equation, make an assumption. Don't make the math harder than it needs to be. Some final notes, guys, is make sure that you are using a balanced equation, working with molarity, and comparing the K value to your reactant concentration. The idea is that if the K value and the concentration are different by an exponent of 3 or more, you're going to get less than 3% error making those assumptions. Okay? Now the other thing I want to say is K's are different. We use K KEQ to talk about the equilibrium K, which is the same thing. We talk about KC, where you're using the equilibrium concentrations to find your KEQ. We talk about Ka, which is the equilibrium of an acid, Kb, which is the equilibrium of a base, Kp, which is using the pressures instead of concentrations. All of these really are just Ks. So just be aware that K can have different subscripts, but it's going to be set up the exact same way. So Kp involves pressures. Now, back in gas laws, we talked about how pressure and moles are proportional. And so we can actually just plug in the partial pressures of each gas to get the K, the Kp for these expressions. So here, if we have nitrogen plus 3 moles of hydrogen reacting to form 2 moles of ammonia, we know that our K here is technically molarity of ammonia squared over nitrogen times hydrogen, cubed. Now, we aren't given molarity, we're given atmospheres. Doesn't matter, you can actually plug them in just as they are. So you get 2.9 times 10 to the minus 2. That is going to be squared because of this coefficient, over 8.9 times 10 to the minus 1 times 2.9 times 10 to the minus 3, and that is cubed. And when you plug that in, oops, again, guys, the key here is you want to make sure that you are entering it in a way that tells your calculator you are smarter than it. So it doesn't matter how you do it, but you should make sure you are getting the right answer here. Don't just assume that you are. And so you should get something like 3.9 times 10 to the 4. If you do not, come see me, talk to me about it. Now, we could talk about the gas laws again here, but I don't want to. Instead, what we're going to talk about is the relationship between K and Kp. This equation is on your equation sheet, and it's just a way of talking about how do you get to K when you found Kp. So you're going to plug in what you have, where delta N is going to be the coefficients of products minus the coefficients of all of your reactants. So if we look, this is 2 minus reactants, which is 3 plus 1 is 4, so 2 minus 4 is negative 2. Gas constant I will give you, and the temperature needs to be in Kelvin, so make sure you're adding 273.15 if you've got it in Celsius. So here, using the Kp value, find your K. 35 degrees Celsius, we're going to convert this to Kelvin, and we get something like 308.15. Gas constant is given, and then coefficients, we have 2 products minus 3 plus 1 is 4 reactants, so N is negative 2. Now, you're then just going to plug this in, and you should get this value. And again, if not, guys, please come let me know. That is it for this unit. We are going to continue to develop equilibrium under acids and bases, and hopefully it'll be just as fun.